Adaptations of connective tissue to exercise. The connective tissues of the musculoskeletal system, tendons, ligaments, fascia, and cartilage complex and dynamic structures. Connective tissue are the critical link between the muscles and the bones through which the movement is facilitated. Routine physical activity can improve the quantity and quality of connective tissue. If the connective tissue becomes the weak link, as in an injury, considerable performance capabilities are lost. A detailed study of the structure and properties of connective tissue provides background that will help the strength and conditioning professional understand how connective tissue transmits force or provide passive restraint on a joint during athletic performance. Collagen fiber. The primary structural component of the connective tissue in the musculoskeletal system is the collagen fiber. The major collagen of bone, tendon, and ligaments consists of the same protein, type 1 collagen. The strength of tendons and ligaments is derived from the internal architecture of the collagen fibers. For further detail, a protein, procollagen, is synthesized and secreted by a spindle-shaped connective tissue support cell called a fibroblast. Procollagen molecules consist of 3 protein strands twisted around each other in a triple helix. The procollagen molecule leaves the cell with protective extensions on the ends of the molecule to prevent collagen fibers from forming prematurely within the cell. Cleavage of the procollagen extension results in the formation of the active or mature collagen molecule that aligns end to end with other collagen molecules to form a long filament. As the molecules line up, they do not actually connect end to end. Rather, a slight gap is left between the ends of the molecules within a single filament. The complete filament then aligns itself side by side with neighboring filaments in such a manner that the collagen molecules in one filament overlap the gaps between molecules in the adjacent filament. The parallel arrangement of the filament is called a microfibril. Collagen has a striated, striped appearance under a light microscope, somewhat like skeletal muscle, owing to the orderly alignment of the gaps between the collagen molecules within the microfibril. The microfibrils become arranged in fibers, and the fibers into larger bundles. The true strength of collagen comes from the strong chemical bond called covalent cross-linking that forms between adjacent collagen molecules throughout the collagen bundles. Finally, the collagen bundles can be bunched together longitudinally to form tendons or ligaments, or arranged into sheets with layers orientated in different directions, as found in bones and the fascia located in skeletal muscle. Their organization of collagen fibers and their incorporation into connective tissue are similar to the organization of muscle fibers in skeletal muscle. It is important to remember, however, that key differences between the two types of fibers: the muscle fiber is a cell with a membrane, sarcolemma, and seals the cell off as an individual existing fluid-filled unit with its own microenvironment. Found within the boundaries of the sarcolemma are nuclei, myofibrils, organelles, and various molecules such as glycogen, all suspended in the sarcoplasm of the muscle cell. In contrast, a collagen fiber is not a cell. It is in the extracellular space, not within the cells, that the collagen molecules align to form collagen fibers. Thus, the complete collagen fiber is not enclosed by a cell membrane, but rather it is not enclosed by a cell membrane, but rather it is a parallel arrangement of protein strands that have been bunched together by the extracellular space because of a mutual attraction, and then chemically cross-linked to form a stable structure. The cells that originally produced the collagen molecules become compressed between the bundles of collagen. Biology of tendons, ligaments, and fascia. Tendons and ligaments are composed primarily of tightly packed parallel arrangements of collagen bundles. Mature tendons and ligaments contain relatively few cells. The small number of metabolically active cells in tendons and ligaments makes the requirement for oxygen nutrients in these tissues relatively low. Tendons and ligaments do not have a direct blood supply, however. Ligaments contain elastic fibers in addition to collagen. These elastic fibers contain elastin, an extensible protein. A certain amount of stretch must be permitted within a ligament to allow normal joint motion, the degree of elasticity being specific to the functional requirement of the joint. Thus, ligaments contain fibers that provide strong structural support, collagen, and fibers that confer a degree of flexibility to the ligament, elastin. Tendons and ligaments attach directly to either cartilage or bone. This union is well designed to resist separation. For example, connective tissue supports cells at a bone-tendon junction, produce both collagen fibers and other essential structural components needed for the formation of tendons and bone tissue, thus creating a blend of the structure at the site of insertion. As the bone grows in diameter, the tendon or ligament insertion becomes buried in the bone surface, increasing the strength of this junction. The fibrous connective tissue that surrounds and separates the different organizational levels within the skeletal muscle are referred to as fascia. Fascia have sheets of fibrocollagenous support tissue containing bundles of collagen fibers arranged in different planes to provide resistance to forces from several different directions. Individual muscle fibers are surrounded by a layer of connective tissue called endomysium. That consists of several layers of proteins that serve to anchor the muscle cell to the extracellular matrix proteins found between the muscle cells. The extracellular matrix proteins are a part of the fascia layer called the perimysium, which connects muscle fibers together into distinct bundles or fasciculi. Finally, all the fasciculi of muscles are bound together by the fascia layer termed an epimysium that surrounds the entire muscle. The different fascia layers found within the muscle converge together near the end of the muscle to form a tendon. It is the tendon rather than the muscle that is attached directly to the bone surface. Thus, the force of muscle contraction is transmitted to the bone through the arrangement of fascia located throughout the muscle. Biology of cartilage. Cartilage is a dense connective tissue consisting of cells embedded in a firm matrix. The unique composition of cartilage matrix renders cartilage capable of withstanding considerable force without damage to the structure. The main function of cartilage are to provide a smooth, articulating surface at the interface of bones and in a joint, act as a shock absorber for forces directed through the joint, aid in the attachment of muscles to the skeleton. A feature unique to cartilage tissue is that it lacks its own blood supply. This means that the cells produce cartilage, the chondrocytes, must depend on diffusion of oxygen and nutrients from a synovial fluid for survival. This unique feature is the main reason why cartilage does not easily repair itself after sustaining a substantial injury. Two primary types of cartilage, hyaline cartilage and fibrous cartilage, are significant to physical activity. Hyaline cartilage is found on the articulating surfaces of bone and thus is often referred to as articular cartilage. The collagen fibers of hyaline cartilage arise from the bone surface perpendicular to the articulating surface of the bone and curve to become parallel to it. The number of collagen fibers, type 2 collagen, present in cartilage is only about 1/2 the number found in comparable quantities of tendons or ligaments. The internal environment of the cartilage matrix within in which the collagen fibers traverse exists as a gel-like material called ground substance. Ground substance is composed of large carbohydrate molecules, glycoaminoglycans, and carbohydrate protein molecules, proteoglycans, that attract a great deal of fluid into a cartilage matrix. Each protoglycan molecule acts as a compressed spring within the matrix. The loose packing of the collagen fibers, the spring acting of the cartilage molecule, and this aqueous environment of the cartilage matrix allows cartilage to accept a large force by temporarily changing shape to dissipate force and then return to its original form. This characteristic allows the cartilage to be compressed during weight bearing or joint movement and then spring back to its original shape when it is stressed removed. Fibrous cartilage is very tough form of cartilage found in the intervertebral disc of the spine and at the junctions where tendons attach to bone. It consists of prominent bundles of type 1 and type 2 collagen fibers arranged in parallel to provide resistance to external forces. Each intervertebral disc is a thick, rubbery pad of concentrically arranged fibrous cartilage layers. The outer articulating surface of the disc is lined with a thin layer of hyaline cartilage, and the deep part of the disc is a soft gelatinous matrix. Intervertebral discs function as shock absorbers, permit limited movement between vertebrae. Effects of physical activity on tendons, ligaments, and fascia. The primary stimulus for connective tissue growth of tendons, ligaments, and fascia in mature adults is the mechanical forces created during physical activity. The degree of tissue adaptation appears to be proportional to the intensity of the exercise stimulus. As with bone and muscle intensities of exercise that exceed the strain placed on the connective tissue during normal daily activities, stimulate connective tissue change in the stimulus it is repeated on a regular basis. Empirical evidence suggests that connective tissue must increase their functional capabilities in response to the enhanced contractile forces created by hypertrophied muscles. The sites where connective tissues can increase strength and thus load-bearing capabilities are at the junction between the tendons or ligaments and bone surface within the body of the tendon or ligament, and in network of fascia within skeletal muscle. Stronger muscles pull harder on their bony attachments and cause an increase in bone mass at the tendon-bone junction and along the line over which the forces are distributed. Such adaptation occurs in the collateral knee ligaments of experimental animals following several weeks of treadmill running. Additionally, animals exercised on treadmills with uneven surfaces have shown even greater tendon-bone junction strength compared to with animals trained on smooth surface. The adaptation that occurs in tendon-bone junctions is quite effective. The point of ligament rupture in animals moves from the tendon-bone junction in untrained animals to within the body of the tendon or ligament after chronic exercise training. A general connective tissue response to aerobic endurance exercise is increased collagen metabolism, meaning that damaged collagen fibers are replaced without a net gain in the amount of collagen in the remodeled tissue. Compared with muscle tissue, the metabolic turnover of tendinous tissue is many times slower due to the poorer vascularity and circulation. This remodeling response indicates that training of low to moderate intensity does not markedly change the collagen content in connective tissue. Conversely, high intensity loading of the musculoskeletal system results in a net growth of the involved connective tissue. Work-induced muscle hypertrophy in animals that follows extreme loading regimes related to an increase in the number and size of the fibroblast cells within the connective tissue of the hypertrophied muscle. Fibroblast activity is also raised, resulting in a greater supply of total collagen availability for incorporation into the fascia of the growing muscle. It is interesting that activation of fibroblasts and the subsequent growth of the connective tissue network are prerequisites for the hypertrophy of the active muscle. An enhanced connective tissue network is probably necessary to withstand the greater force capabilities of growing muscle. This relationship may explain why biopsy studies on trained athletes have shown that hypertrophied muscle contains greater total collagen, but the collagen content remains proportional to the existing muscle mass. Specific changes within the tendon that contribute to the increase in the cross-sectional area of strength response to a functional overload include an increase in collagen fibril diameter, a greater number of covalent crosslinks within the fiber of increased diameter, an increase in the number of collagen fibrils, and an increase in the packing density of collagen fibers. Together, these adaptations enhance the tendon's ability to withstand greater tensional forces. Effects of physical activity on cartilage. The response of articular cartilage to physical activity may seem less obvious. However, the fact that articular cartilage gets its nutrient supply by the diffusion from synovial fluid links joint mobility to joint health. Moreover, a bowed joint creates changes in pressure to the joint capsule that drive nutrients from the synovial fluid towards the articular cartilage of the joint. Immobilization of a joint prevents proper diffusion of oxygen and essential nutrients throughout the joint, resulting in the death of the chondrocytes and the reabsorption of the cartilage matrix. These changes may become irreversible if a joint is immobilized for too long without periodic passive mobilization of the joint through its full range of motion. However, mobilization of a joint prior to healing is the articular surrounding can be damaging to the joint. Further support for the positive effects of weight-bearing activity on articular cartilage is evidenced in a typical knee joint, whereas the surfaces of the joint that experience the greatest degree of weight-bearing are thicker than the non-weight-bearing surfaces. Complete movement throughout the range of motion of the joint and weight-bearing forces seem to be essential to maintaining tissue viability. Animal studies to evaluate the potential negative effects of chronic aerobic exercise on articular cartilage have shown encouraging results. Long-term adherence to treadmill exercise in guinea pigs thickens the cartilage and increases the number of cells and later the total ground substance present in the articular cartilage. Running studies using dogs as subjects have demonstrated that a moderate running program, 2.5 miles per day, 5 days a week for 40 weeks, increased articular cartilage thickness, protoglycan content, and indentation stiffness. It was also found that more strenuous running, increased to 12 miles, decreased cartilage thickness and protoglycan content. Note that running 25 miles per session for 1 year also decreased protoglycan concentration, indentation, stiffness, and stimulated remodeling of subchondral bone, but it did not lead to degenerative joint disease. Even weighted running, using weighted jackets weighing 130% of the animal's weight, of 2.5 miles, 5 days per week for 550 weeks has not been shown to cause degenerative joint disease. Conclusion. The musculoskeletal system is sensitive to changes in a person's level of physical activity. Exercise training has positive effects on bone, muscle, and the associated connective tissue. The entire musculoskeletal system undergoes a coordinated adaptation to exercise. The overall function of the system is based on the intimate linkage of the contractile tissue, muscle, and non-contractile support tissue that establishes the framework through which the forces created by muscular contractions are transmitted. Healthy people undergoing strenuous exercise training experience changes in the force-generating capabilities of muscle, resulting in the coordinated and proportional increase in the load-bearing capacity of bone and other connective tissue. Exercise training can increase skeletal muscle mass, force-generating capabilities, and metabolic capacity. Changes in the collective properties of muscle fibers are specific to the metabolic and force requirements of the activity. Some of the most important ways in which muscle fibers increase aerobic and anaerobic capacity are the enhanced enzyme profile, an increase in the number of key organelles such as mitochondria, an increase in the storage of various substances, and the increase in the amount of contractile proteins within the cell. Bone and other connective tissue show a more general response to increased physical activity. The extent of tissue adaptation is related to the degree of deformation experienced by the tissue involved in the activity. That is, the intensity of training. Connective tissue changes consequent to higher intensity exercise training include increase in the number of collagen fibers and the strengthening of individual collagen fibers through an increased number of covalent cross links within the fiber. In bone, there is an increase in the amount of mineral deposition in the collagen matrix, and in some instances, a change in the geometry of the bone.